The second, part B, is finding an improved appropriate step size, alpha k. Since yk plus 1 equals to yk plus alpha k times dyk for all the alpha k greater than 0, so d is greater than 0, so therefore it is still maintained in the relative interior for that. So we're going to find out for each one of the di elements in d vector, for some I, then we will try to find what is the largest step size alpha k can go. And we know that the dyk is, y is currently 1, and dyk is after negative ck after projection. So the largest alpha k can go is yik divided by negative dyk for its ith element, and the yik is actually 1 right here. So this is basically followed our minima ratio test. Now alpha k equals the minima of all the gamma k divided by negative dyk for dyk of I is less than 0. If dyk is I is greater than 0, it doesn't matter. It will never violate the non-negativity constraint. And what is gamma? Gamma is supposed to be 1 right here as this. The gamma is something slightly less than 1. So we keep, after that next step, we still maintain in the interior of the feasible region in that case. So frequently the gamma was chosen to 0.9, 0.99, 0.95, and many times people using try and error to figure out what is the best gamma to use. So by using a similar concept of a minima ratio test in the y domain, which is after the affine transformation, I can easily calculate the step size of alpha. And the next, part C, is trying to calculate a new solution in an x space instead of y space. And we know that yk plus 1 equals to yk plus alpha k times dyk. So it's actually inverse transform back, we can calculate xk plus 1. Okay, and that's fairly simple once we multiply the y domain in front of xk, capital Xk. I can have a xk plus alpha k times xk times dyk. Okay, and this is fairly simple as well. I can calculate the dy using this equation. Okay, dy is actually calculated on that with a negative sign from, and we can put out the entire P matrix, calculate that way, and xk equals to alpha k times capital Xk squared minus c, actually c is right here, times A transpose times A times capital Xk squared times A transpose inverse times A times Xk squared times C. So this part is fairly simple. What we can do is xk minus alpha k times capital Xk squared minus C minus A transpose times omega k. And omega is actually the do variable solution, do variable. And this value can be calculated by the yellow part up here. So omega k equals to A times capital Xk squared times A transpose inverse times A times Xk squared times C. So now we have a fairly simple result. Xk can be calculated by xk plus 1 can be using the current x minus alpha k times xk squared minus the cj minus zj, basically. Here we going back to the linear programming. C minus A transpose omega should be z, basically. And the omega can be calculated this way. So even though the process looks a little bit messy in the beginning, but the result is very straightforward and easy to calculate each iteration. Hence, we can also define the improving and feasible direction for the x, we call it dxk instead of dyk, equals to negative xk squared times the c minus a transpose times omega k. And dyk can be defined accordingly as well. Okay, so basically dyk, each j elements equal to x kj of zj minus cj. So this is very similar to basically skilled zj minus cj using the current solution xk. Okay, so this solution, the result is very nice and easily to implement. So that's why we say the primal affine scaling method, even though the concept is a little bit more complicated and the calculation is a little bit involved. However, it is the result itself is fairly easy to implement in that sense. Okay, we can calculate the dyk and make sure the calculation and the dyk is basically can be defined as before, and we can verify the objective function z hat k plus 1 is the original z hat k, which is the original objective function, minus a definitely positive portion of that. So we guarantee with the definition of dyk squared, and this term will be always negative. This term will be always negative because this term is always positive. Alpha k is positive, dyk squared is also positive. Okay, so positive times a positive is a positive, and with a negative sign in front of that, this definition of dyk, we can guarantee the objective function value actually decrease at each iteration. Okay, couple things we can the step. If xk belongs to P0, P0 is the relative interior of the original feasible region, and dyk is greater than 0 for all the elements, and then we can conclude the P1 is unbounded, since we can go follow the dyk direction, go as far as possible. So alpha k is infinity, basically. If xk belongs to the interior of the feasible region and dyk equals to 0, and then we know the current solution xk is the optimal solution, and we stop the algorithm. Okay, if P1 has a finite optimal solution, the sequence generated by the primal affine scaling method, ck times xk, is well defined and strictly decreasing because this portion of the solution, negative alpha k, is positive, and dyk squared is also positive with a negative sign. Each iteration we will decrease our objective function for sure. Okay, and we can define the duality gap, which is the primal objective function c transpose times xk minus the dual objective function, which is b transpose times omega k, equals to e times xk, which is what? Inverse transform of y back to x times s. Okay, the s is basically c minus a transpose times omega k equal to s. So the duality gap is also well defined as well. And we can easily calculate dyk equal to xk minus times sk inverse. So now we are summarizing the primal affine algorithm. First, set the k equal to 0 and find the initial solution x naught is strictly positive and satisfy the current constraint a times x naught equal to b. Okay. Second, we compute the due solution. Okay, we can compute the due solution, omega k and sk. The sk equals to what? C minus a transpose times omega k. And once we have the sk, I can easily calculate dyk equals to negative capital xk times sk. Okay, so now the calculation of dyk is much more simplified. and streamline. So even though we are working in the Y domain, okay, actually the calculation is fairly straightforward. Step number 4 is checking the optimality condition. If current solution is in the relative interior of the feasible region and dyk is strictly positive, okay, then stop. The problem is unbounded. If sum of the E transpose times dyk is less than a small epsilon, which is the convergence tolerance, and sk is all non-negative, then we stop. We have the optimal solution on hand, at least close enough optimal on hand. Otherwise, we're going to go to the step 5. Let's look at the step 5 in the next iteration, next slide. The step 5 is calculated step size using the minima ratio test. Okay, for all the dyk IC element is less than 0, we calculate gamma divided by negative dyki and see which one is minimal. So this is typically the minima ratio test, and our gamma is usually a number close to 1, 0.9, 0.95, 0.92. Many people try different. Then after that, after I determine alpha k, I can actually update xk plus 1 by xk plus alpha k times capital Xk times dyk. Then we update the iteration number k to k plus 1, and then we go back to step 2 to recalculate the due solution and the due slack. Okay, I would this will conclude this section of the lectures, and basically on theory portion. I know the original concept and the domain transformation and the projection matrices are a little bit more involved and complicated. Looks complicated, but actually the result itself is very easy to implement. Okay, in the next lecture, we will actually demonstrate and present a numerical example to walk you through all these steps and show you how easy it is to perform this Primal Affine scaling method. The Primal Affine scaling algorithm is the original idea developing from the Karl-Markov algorithm. It's basically a simplified version of a Karl-Markov algorithm developed in 1992. Okay, and people think this version is super easy to implement. Actually, you can use this as one of your term project to write a computer code to execute this. And if you follow this step, we have presented in these two slides, the last two slides, 13 and 14. And you should probably figure out this is very, very easy as long as you have the method to calculate matrix multiplication and the inverse of a matrix easily. And this matrix A times X, capital Xk squared times A transpose is a square matrix, and using the as a symmetric also. So calculating the inverse is fairly straightforward. All you have to do is do a so-called Cholesky factorization. We'll talk about those computational effort later on and how easy it is to implement. So several existing programming language like MATLAB or Python, NumPy, or R programming language can be easily used to implement these algorithms with a very small number of lines of code. So you're welcome to implement this. And next lecture, we're not going to waste too much of your time, but we trying to present the algorithm and theory first, then we present a numerical example next. Okay, thank you.